Vector search alone is not enough when results must match metadata. Qdrant Payload filters let you search by meaning and conditions together. You'll learn the shape of a workflow that searches by meaning while enforcing required document details. I'm Professor Pi, teaching AI foundations with simple Python. Vector search finds similar meaning, but many applications need more than meaning. You might want recent items only, or content from a trusted source, or items owned by a particular user. Without both checks, your semantic hits can drift into the wrong scope. Qdrant stores both vectors and payload metadata. Its filtering lets you combine a semantic ranking with exact or ranged metadata constraints, so results are both relevant and valid for the business rule. The intuitive idea is simple. Imagine searching for policy notes about security. You embed the query and search by vector similarity. Then, you also require that the document comes from the doc source and belongs to the requesting user. Success means the top hit is about security and also fits those rules. The weakness is that payload filters limit the candidate set. So if the filters are too strict, you might get no results. Pick practical filters and test them. We will build a small demo that shows the whole loop. It will open a local Qdrant client, create a tiny collection of 3 vectors with payload metadata, insert those points, run an unfiltered vector query to show the drift, and then run a filtered query that enforces ownership and recency. That sequence makes the motivation clear before we add constraints. Quick note, this code is designed to teach the core idea clearly. Library versions and local setups can vary, so check the official docs if your setup behaves differently. First, we make sure our Python client can talk to a running Qdrant instance and list collections. This snippet gets a live Qdrant client and proves the connection works before we do anything else. QdrantClient points at the local service. Collection becomes our shared name for storing vectors and payloads. And getCollections is a tiny smoke test that confirms the client can reach the server. The visible output prints the current collection count, so you can see the connection path is valid. Now that the client talks to Qdrant, we need a place to store vectors and payloads that defines vector size and metric. This example creates the collection that will hold vectors plus payload metadata, so later inserts have a well-defined home. The collection declaration sets the vector shape and similarity metric up front. Models.VectorParams with size equals 3 and models.Distance.COSINE. We're using tiny vectors here to keep the demo readable on screen. In practice, these would come from an embedding model. Collection exists, double-checks Qdrant accepted the definition, and the visible output shows the collection is ready for writes and queries. With the collection ready, we insert a few points that include both vectors and payload fields for later filtering. This code writes 3 Qdrant point struct records that carry both semantic vectors and payload keys you can filter on. The vectors give a rough semantic direction, and the payload contains fields like cat, src, user, day, and title that encode ownership and source rules. Note that ID equals 3 is semantically close to security, but belongs to user U2 and comes from forum, not docs. Client.upsert sends the points, and wait true makes the write visible immediately. The visible output reports how many points were loaded and confirms Qdrant finished the write. Next, we run a plain vector query to show why similarity alone can be misleading for constrained apps. This snippet runs an unfiltered vector search so you can see retrieval drift in action. The query vector 2 points strongly towards security content, so query points ranks the nearest security-like vector first. But that top hit can still violate app boundaries, because payload rules such as user ownership and source aren't part of vector distance. With payload equals true lets us inspect the return scored points metadata, and the visible output shows the unfiltered top result belongs to U2, exactly the kind of mismatch filters are meant to stop. Now we add a filter and rerun the query, so the result is both relevant and allowed by metadata rules. This example scopes the vector search by adding Qdrant filter conditions, so the top result is both semantically relevant and allowed by metadata. The EQ helper builds field condition objects with match value for exact rules, while the day condition uses models.range to require a recent enough record. Passing query filter scoped applies those payload constraints, and Qdrant still ranks by vector similarity inside that allowed set. With payload, limits which metadata fields are returned for display. The visible output shows the selected title and day, proving the chosen hit matches the meaning and the required metadata boundaries. This demo uses a tiny setup to show the full pattern and how payload filters change retrieval. In a real system, you'd swap in real embeddings, larger collections, and then measure how tighter filters affect recall and latency. The same filter logic works for tags, access control, sources, or time windows at much larger scale. But remember, make filters practical and test their impact on results. What this is, when to use it, and one caution. It's a vector plus payload workflow that enforces metadata constraints during search. Use it when semantic relevance must also respect ownership, source, or recency. And watch out, if your filters are too strict, you can end up with empty answers. A practical next step is to experiment with the similarity metric in this pipeline. Try swapping models.Distance.COSINE for a different metric and compare the top filtered hit. That single change shows how distance choice interacts with payload scoping on your data. If AI Foundations in Python help, subscribe and watch the AI Foundations videos.